Well, good morning. This is Wednesday morning. Well, we got somebody here, but he's not one of my students. Okay, what you need? This is Cal 1, one of my larger classes.
Okay, well, Richard's not here.
Huh?
I came looking for Richard.
Oh, I see.
Sorry.
Well, I'll say larger. It's supposed to have 5 in it.
Oh, okay. Go ahead.
And,
Sorry, I didn't mean to.
and Monday, 4 out of 4 was there. One I've never seen. I've seen him in the hall, but not in class.
Maybe that's running late.
I guess so. Okay. You need a key?
Sure.
Okay.
All
All right.
Can we sit in here and do calculus with you?
Yeah, I'm just going to report. So, in fact, when you came in, I thought, I finally have a student, but no, I don't.
I can do
A former
calculus with
student.
you if it makes you feel better.
Okay. All righty. Okay. That was not one of my Cal 1 students. That was a previous student. But anyway, I'm here in the classroom at 9:35 in the morning on Wednesday, the 8th of February, 2017, Calculus 1, and I'm the only one in the room. There was somebody else came in, but he wasn't a Cal 1 student. So I guess we'll pick up and go from where we left last time. Normally I would say, if you had any questions, no one's here, I can't ask you if you have any questions. So this example is evaluating a limit by changing the variables. Okay? Now, it's okay to change variables, but I don't think you actually have to. It says to investigate this limit. Let me get my pen activated here. Dark blue. The limit as h approaches 0 of sine of 4h divided by h. Okay? Now that looks suspiciously like one that we did before. I'll find it in a minute. This one. The limit is sine as theta approaches 0 of sine theta over theta. We know that's 1. That is an important trigonometric limit. We know that one. You should have that one down. This isn't quite the same, however. Okay? This is sine 4h over h. Well, how to get this to look more like the previous one is multiply the numerator and the denominator by 4. Now you got sine 4h over 4h, which we know that limit is 1. The 4, that's just a constant. You can bring that on the outside, and that's 4 times the limit. Now here's what the book does. They change the 4h to be theta, okay? And if 4h is theta, as h is going to 0, then theta is also going to 0. I don't think it's necessary to do this, but you can. And that theta is going to 0, and the 4 is on the outside, and then this would be sine theta over theta. And basically our substitution here was let theta equal 4h. Then, as h is approaching 0, theta is also approaching. Theta is also approaching 0. Putting 0 is approaching theta. 0 stays 0. Theta is also approaching 0. Okay? And then this is 4. Now, that's sort of the easy way to do it, is just multiply numerator and denominator by 4. You see that's the form that is going to 1, because this entity here, by that one that we went back is 1, 4 times 1 is 4. They also did this as you let h equal, say, 1. That's pretty far away, and whether it's plus 1 or minus 1, sine, if h is positive, the sign is positive. Let's see. Positive 1. 1 is in the first quadrant. Okay. So positive 1. Sign is actually, that's not quite true. Okay. When h is 1, 4h is not in the first quadrant. It's in the let's see, 4. See, 1 is about 1/3 of a pi, so this would be 4/3 of a pi, and that would be over there in the third quadrant, and sign is negative there. So h would be, h is plus 1, 4h is plus 4, sine of 4. It doesn't matter. It's a long way off from 0, so you're not even close, but that's why it's negative. And then when you put a minus 1 in there, sine of minus 4 would be back in the second quadrant, and that would be positive, but your denominator, h, would be negative, so that would be, again, negative. So that stays the same. Basically, you have an odd function over an odd function that produces an even function. Plus or minus 0.5, that gives you, that's more like close to 30 degrees, or pi 6. And 4 times, well, I'll take their word for it, it's 1.181. Okay, but still, you're not really all that close. Plus or minus 0.2, you're getting at 3.5. Plus or minus 0.1, 3.8. Plus or minus 0.05, 3.97, blah, blah, blah. 3 plus or minus 0.01, 3.99, blah, 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 blah. And plus or minus 0.005, 3.999, blah, blah, blah. And sure enough, that's getting closer and closer to 4. So as you approach h equal 0 from either the right or the left, plus or minus side, or the limit does get closer and closer to 4. But this does it much faster than plugging in all those numbers. All right? Now, let's do example 3. I think I'll clear this off the slides. And now we're doing the limit as x approaches 0 of the tangent of 3x divided by the tangent of 2x. Okay? For some reason put them in parentheses, that's fine. You don't have to, but I guess it makes it clearer. Okay? Now, I guess before we do anything else, we ought to plug it in. Well, as x is approaching 0, 3x is approaching 0, tangent 0 is 0, but so is 2x approaching 0, and tangent of 0 is approaching 0. So you got it in the undeterminate form, indeterminate form. So we don't know. We're going to have to do some other manipulations here. Okay, and I guess the one that would first come to my mind, don't know if this is what their suggestion, but let's do the limit as x is approaching 0, and tangent 3x would be sine of 3x over cosine of 3x over sine of 2x over cosine of 2x. Okay. Now, as x is approaching 0, that numerator is 0, approaching 0, and the denominator's approaching 0. It's still in the same boat you are, but if you break it down, that would be a 0 over 1, because as x is approaching 0, cosine, or 3x is going to 0, but cosine is approaching 1 in both numerator and denominator. So, not real clear whether that's helpful or not, but it certainly does introduce something that's not going to 0, but still the sine 2x is going to 0. So that hasn't really helped us big time unless and until we do this, the limit as x approaches 0 of sine 3x over cosine 3x times, when you divide a fractional form, you multiply by the reciprocal, so it'd be cosine 2x over sine 3x. Okay. Now, the first one is approaching 0, as we said. The second one is not an indeterminate form. That's just not even allowed, because that would be some number 1, basically, over 0. So we don't want to let that derail us yet. But what we can do here is, and this is sort of a trick. It's not something I'm not sure any of you would have thought on your own. I'm not sure I would have thought on it on. Let's multiply numerator and denominator here by x over x. But that's an indeterminate form too. But what does that give us? Okay. Okay. I'm not sure I would have chosen x over x. In fact, I see an error I made here. Sorry about this. That's a 2x there. I think I said 2 but wrote 3. Or maybe I said 3, but that's a 2x there. Okay. My denominator was that. I'm not sure if this really gets us anything big time here. I think if I were doing this, I would have multiplied by 3x over 3x. And then while I'm at it, maybe also multiply by 2x over 2x. Those are both 1, so it's legal to do, but why would I go to that kind of effort to do this? Well, here's why. That limit, as x is approaching 0 now, I'm going to take the 3x, the sine 3x here, and put it over the 3x there. So I'm going to group these two together. Okay? Then I'm also going to group these two, sine 2x with 2x on top. Those two together. Okay? And what does that leave me with? Okay? I get no benefit in putting the cosines over or under, 3x's or 2x's, so I don't want to group those together. So what I'm going to do now is cancel out those two x's, and that leaves me a 3/2. Okay? Divide out those two x's. Okay? And that leaves me a cosine 2x over cosine 3x. Okay. Now, we know that the 3/2 can come out the front. 3/2 times the limit as x approaches 0 of, I know this limit. That's 1. So, 1. Now, I contend to you if sine of 2x over x, sine of 2x over 2x is 1, then 2x over sine x, or sine 2x, that also should be a 1. Okay? And then as x is approaching 0, 2x is approaching 0, cosine is approaching 1, and same with the denominator. this would be 1 over 1, which is 1. So I contend to you this is just 3 halves. Okay, let's see. Yeah, that's what they got to. Okay, and that's exactly how they approached it as well. Now, I don't see why they did x over x. It seems like it would have made sense to do a 3x over 3x and a 2x over 2x. Okay? This is getting pretty boring, but still no one showed it.
Yeah,
Okay.
Richard's not doing well.
Oh, is that true?
Yeah, he's going home.
Yeah. Okay. I guess the other 3 or 4 must not be feeling well either. I thought I saw one walking down the hall, but it was too far away. I couldn't pick her out. I thought it was one of the students, but she never showed, so I guess not. So, exciting times.
I'm gonna go be bored while you're bored.
Okay.
I can't do anything because I have a literature class scheduled for right now.
Oh, that's true.
And
Okay.
I can't do
And
anything.
it was canceled, huh?
Yeah.
Oh, wow. Yeah. Okay, well, enjoy.
She want me to do calculus.
Right. Well, you're welcome to sit in if you want to, but it's up to you. All right, but that does finish 2.6. Okay. The Argonne said, okay, good deal. I have a student. Okay, do you want me to project them?
Maybe if I roll up the room, somebody else will show up.
Okay. Normally we do the preliminary questions. Since y'all aren't here, what I'm going to suggest to you is do them, and if you have any questions about them, bring them to class and I'll answer those questions. Okay? Homework exercises then from 2.6 would be, I think I assigned some of these before, do any of the odds 1 through 5. Do any of the odds 7 through 15. Do any of the odds 17 to 25. Do 27. Only one like that. And I don't think I assigned one like that before, so do 27. Then do any of the odds 29 through 47. Then do either 49 or 51, or both if you choose. And then do either 53 or 55, or both if you choose. Okay? And that's all from that. You can look at the further insights and challenges. If you want to do any of those, you certainly can. So that finishes, I think. Oh, remember that example 2? I didn't realize they did the at least one step in the solution here. So I did it on the board, and this is very similar to what I did, but I want to see it in a little bit clearer print. We don't have a rule for sine 4x over h, 4h over h is h equals to 0. We do have sine theta over theta. So if we get these two things the same, then we do have a rule for that. So let's multiply the denominator by 4, but then we have to multiply the numerator by 4 as well. And then they did the substitution here, let theta equal 4h. So then you would have sine theta over theta, and if h is going to 0, 4h, which is theta, is also going to 0. So then I would have already pulled the 4 from the outside, and that, yeah, they did it here. 4 times this limit here, we know from before, is 1. Okay. Same thing we did, but maybe a little bit different order. Okay, and that finishes the 2.6 slides. So let's move now to 2.7. What I think what I typically do on 2.7 is just go over it with you, because quick slideshow of it, because, but I don't think I'll test you on it. The main reason, it's a very short section, but it's limits at infinity. And I guess sometimes that is something that might make sense if it'll ever come up here. There it comes. But basically, you usually take limits to some finite number. But there are times and circumstances where maybe doing it at infinity. But infinity is not a number, so don't get confused, okay? It's not a number. So it says, so far we have considered limits as x approaches a number. C is also important to consider limits where x approaches either positive or negative infinity, and we refer to this as limits at infinity. In applications, limits at infinity arise naturally when we describe long-term behavior of a system, okay? So this notation as x approaches infinity indicates that x is increasing without bound, or that as x approaches negative infinity, it is decreasing through negative values without bound, okay? So we use the terminology here, but here is kind of an example. This is the Earth's average temperature. See if I can blow this up. Yes, I can get it all on one slide even, I think. Okay. The Earth's average temperature, according to a simple climate model, in response to a 0.25% increase in solar radiation, according to this model, the temperature as T approaches 0 will go up from the T approaches infinity. Let's just assume that our average temperature is 283. Now this is in Kelvin, okay? 283 currently. And if it went up, fantastic. Got our first student for the day. You're welcome to stay if you'd like, but he was keeping me awake or something.
Warmed up the room for it. That's all we need.
What's that?
So just needed to warm up the room.
All right. Well, it worked, I guess. So there it is here.
Got you a student. I'm going to go.
Okay. He's tired of this mess, okay? He already had to sit through it once, okay? Twice. Okay. I am pretty sure I'm not going to test you on section 2. We finished 2.6 before you got here, and 2.7 limits at infinity. I'm going to go over it in case you ever need it, okay? But I don't think is as important as when you're actually approaching the limit. But here is according to some simple climate models, if you started at let's just assume this is our current average temperature, 283K, okay, which is Kelvin temperature, and you were to increase the solar radiation by 0.25%. A quarter of a percent. A quarter of a percent. Very small amount. According to this model, that would raise our temperature to, guess what? Strangely enough, a quarter of a degree K. Or not, you don't say degree with K. Quarter of a K. Now, that's rather bizarre. It comes out exactly like that, but it does. Well, what does a quarter, and that's the same as a degree Celsius, increase in temperature do for you? That melts a little more ice, okay? And it just sets a whole new equilibrium. Now, it doesn't happen immediately, okay? It happens starting here. After 5 years, you would be, say, 283.21 or 2. 10 years, you'd be close to 0.25, 15. And this is a little bit greater than 0.25, but there is a cutoff there. And after a while, you're close enough, you could say that around to, say, 0.255. Sorry. It would be 283.255. Now, I can almost predict what I hope are some of the questions that are going through your head. Okay? As t is approaching some number, if you had some expression, temperature is a function of time, then yeah, you could plug in this number in there, see if it works. If it came out in an indeterminate model, then you do other things. But how can you plug in an infinity? Okay, you really can't very well unless you can manipulate it to change a variable to do a 1 over t, which would then be, as t approaches infinity, 1 over t would be approaching 0. And if you can manipulate things that way, yeah, you might be able to do it. So that just indicates some of the little techniques we may use. I'm not going over the whole section in gory detail, but I will show you some graphs. This is one, how just a small amount of increased solar radiation would change temperature, not by much, but by a little bit. But that is, on a big scale, could mean some significant warming. Not a lot, but a little bit. Okay? Here's another example of a function. And they don't give the function. They just say, imagine there's a function y is equal to g of x that does the x like this. Okay? Now, we don't know what your x's are representing. We don't know what the y is representing. We don't know what g is. But let's just say this is a function here. Okay? And most of the time in normal situations, you might see this function. I don't even know if you're interested in very many negatives, but if you were, you're not sure what's happening back here. But you see a lot of weird things happening there. But if you don't go much past 200 or 300, it's not clear what this function is doing. But then if you let it go on out and let the t's or the x's get quite large, positive or quite very small numbers negatively, then you see, sure enough, you have two different asymptotes, horizontal asymptotes, as t is approaching, as x is approaching in positive infinity, then you're going toward 7. As x is approaching negative infinity, you're going toward 3. The interesting thing is that you've actually exceeded 7. But remember, for horizontal asymptotes, you can cross an asymptote horizontal. Vertical asymptotes, you can't touch it, you can't cross it. Horizontal asymptotes, you can. So even though this did exceed that, in the long run, okay, this looks like between x equals 140 or 50 up to 200, well, not quite that way, but you really exceeded 7 by quite a bit, but it came down fairly quickly and then approached 7 from the bottom side, whereas over here for smaller x's, it actually got below 3 and then approaches 3 also from the bottom side. But in the long run, as x is approaching positive infinity, it's going to 7, negative infinity, it's going to 3. Frankly, I can't imagine what function that would be, but it's doing all sorts of weird things in between, and this is probably where you normally operate. But in the long run, you're going to 7, long run towards negative infinity equals 3. Okay? Now, sometimes functions, and you're probably familiar with these, might have a limit as you go, say, negative, but don't have a limit as you go positive. For instance, e to the x. No limit there. There's not even a vertical asymptote there. It's just increasing without bound as x increases. But as x gets very large negatively, it's going to 0 and goes toward it really quickly, but never gets there. So it does have a limit as x goes to negative infinity, but no limit as x goes to positive. Now here's a sine function. No limit anywhere, okay? Not toward an infinity, because there's infinity that just continues going up and down and up and down and up and down and up and down between plus or minus 1 forever. Same way with positive infinity. So this would have no limit as x goes to positive infinity or negative infinity. This has a limit as x goes to negative infinity, but none as it goes to positive infinity. So, what's that? Say that one more time. Okay. No limit. The limit does not exist. Okay. Now this one you could say it's going to positive infinity, but that's not really enough. That limit doesn't exist. Okay. This is going to 0. Okay. This you can't say it's going to any particular value at all. It's certainly not going to positive negative infinity because it always stays between plus or minus 1. That's nowhere close to positive or negative infinity. In that direction and this direction, it just keeps oscillating between plus or minus 1, so there is no limit. You can't get an x large enough to say for x certain size, you guarantee that the function value is always between two values, except plus or minus 1. And that's a pretty big thing, but you can't get that arbitrarily close to any small number. It just doesn't happen. It just stays between plus or minus 1. As large as you go, positive or negative. So that has no limit as x approaches infinity, either positive or negative infinity. Okay, good question. Okay. Here's theorem 1. Sorry, my throat was getting very dry in my first class, and I know technically maybe we're not supposed to eat or drink in class, but I don't object if you do, but I had to bring a glass of water up. I didn't have to, I chose to, sorry. Yeah, especially when I had no one in class, I thought, if I'm going to sit and talk to myself, I'm going to have something to drink. All right, here's theorem 1. For all n greater than 0, as x approaches positive infinity, the limit is x to the nth power, where these are positive n's here, okay? That's going to infinity. The power functions as long as n, and remember n isn't necessarily an integer, is any number greater than 0. As n goes greater than 0, for any x going greater than 0, going toward infinity, the limit. There is no limit. I don't like to say the limit is infinity. The only thing this tells you is going to a positive. It's going arbitrarily great. Now, however, the limit as n approaches infinity as x to the minus n. So in other words, 1 over x to the n, if x to the n is getting infinitely large, 1 over x to the n is getting going closer and closer to 0. Because as your numerator gets large, your whole fraction goes large. But when your numerator is going small, the denominator is going large, numerator stays constant. That's going to 0. So you can talk about this, and that's why I said if you can change your variable and get that x to the n in the denominator, then you know it's going to 0. Now, if n is a whole number, in this case, it doesn't mean any real number. It's now a whole number. What are your whole numbers? 0, 1, 2, 3, 4, 5, the counting numbers with 0. The limit as x approaches negative infinity of x to the n, that would be x to the minus n, which is 1 over x to the, wait. X is going to negative infinity. Sorry, x, not n. Okay, sorry about that. I'm thinking n. X going to negative infinity. So this is a very, very large negative number, but n is a positive number. Then you have strange activity going on. Remember, n can only be whole numbers. If that n is an even whole number, then and x is a negative number, anytime you raise a negative number to a even power, it goes positive. So that's going to positive infinity if n is even, and it's going to negative infinity if n is odd, because you raised a negative number to a very large positive odd power, it stays negative. Okay? But it goes to infinity. Now, this requires n to be a whole number. If you start allowing n to be fractional numbers or other things, you've got just a mess on your hand. Terrible mess. Don't even go there. Okay. Now, the other hand, the limit as x approaches negative infinity of x to the minus n, and again, n is a whole number. So that'd be 1 over x to the n. Well, guess what? Whether x is going to positive or negative infinity, 1 over x to a raised to a power, and as x is going infinitely large or small, this is still approaching 0. It may be approaching 0 from the minus side rather than the plus side, but it's fine. But actually, if n is even again, this would be approaching 0 from the positive side, and if odd is approaching 0 from the negative side. But it doesn't matter. They are approaching 0. Okay? For very large numbers raised to any power. Okay? But the number is allowed to get larger and larger and larger. Okay. Now, this is sort of an example of what we were just looking at. I can't get them all on, so I'm going to start with this part here. Okay. This is as n is even. You're familiar with this, I hope. Here's your parabola when y is equal to x squared. Okay. Now, certainly, as n goes to positive infinity, x goes to positive infinity, your y is going to positive infinity. As x is going to negative infinity, your y is still going to positive infinity because it's an even group. So that's why that second or the first, go back to the theorem, you'll see in a second. If you have a larger power, and x is going even faster. Notice what the larger power does. It flattens it out between minus 1 and 1, but it makes it much steeper outside of plus 1 and minus 1. So they're still going to positive infinity, but actually going there much faster than they were when it was a 2, a 6, an 8, a 10. After a while, you've almost got a square box. It's not quite. It's always curved, but you're going up very, very rapidly. But if your n is odd, if you go to positive infinity, say x cubed, and let x get quite large negatively, that's going to negative infinity. X large positive is going to positive infinity. X to the fifth, again, it flattens it out more between minus 1 and plus 1, but makes it much steeper if you increase your odd power. Makes it much steeper outside plus or minus 1. It's going to minus infinity to plus infinity even faster. Okay? So really it doesn't matter what the n is, as long as it's odd, the limit is x to the n for odd n. As x goes to positive infinity, it does go to positive infinity, but if it goes to negative infinity, the x to the n goes to negative infinity as well. So both of these, if you're this part is true for both of these, whether n is even or odd. But what differs if n is even, that's going to positive infinity, this is going to negative. And n has to be integral value, a whole number of values actually. Okay, here's limit 2. What if we have rational functions, ratios of functions? Now, actually, I think you hit pretty close to this in pre-calculus algebra, okay, when you dealt with rational functions there. The limits at infinity of a rational function, the asymptotic behavior of a rational function depends only on the leading terms of its numerator and denominator. It doesn't matter what these lower terms are doing. Find the maximum exponent in the numerator, the maximum exponent in the denominator, the limit of the behavior of these ratios of these two polynomials, which make up a rational number, is limited by those leading terms. Okay? So what you do, forget about these. You can factor out the a sub n, b sub m. Factor that out, and then it's x to the n minus m. Okay. That's what matters. And this is whether x is going to positive or negative infinity. Because remember, these are all integers for these to be polynomials. The n and m are all integers. Now, let's think about what we've already discussed. If n is greater than m, then this is going to be a positive number that's going to an infinity. Okay? And again, if it's an even positive integer, it's going to positive infinity. If it's odd integer and x is going to negative infinity, this will be going to negative infinity. But they don't exist. If n is equal to m, that is 0, x is 0 is 1. The limit is 1, so the limit would be the ratio of your leading coefficients. That's all. If these two have the same degree, it's that ratio. However, if m is greater than n, now remember they're both integers, then this is a x to the negative p, or whatever you want to call it. It's going to be a negative number, and the limit that for that we saw from the last one there is going to 0. So you already did that back in, I don't know if you remember when you did two. Did you do your pre-calc here? Pre-calc algebra. You did section 2.6 was rational expressions, and you basically went through those things. The calculus here makes it a theorem, not just a rule, but a theorem. Okay? Same theorem you had before. All right. Now, you know what? There is a missing slide. Oh, wait, no, there wasn't. I forgot to do it. I forgot to move down to here. Sorry, I forgot to do this one. Okay. We did those two because I couldn't get all three of them on the same slide. I forgot to go back and do the third one. What's the limit as x approaches positive infinity for 1 over x? As x is approaching positive infinity for 1 over x, that's going to 0. As x is approaching negative infinity for 1 over x, it's also going to 0. Just going from 0 from the top side here, from the bottom side here, but guess what? Still going to 0. Okay. Forgot to show that. It was on the slide. I just blew it up or zoomed in. I lost that on the previous one. I forgot to go back to it. Okay. Flipping the page over here. Actually, since you had it before, I think I will go over it, example 2, even though I don't think they do it on the slide set. No, they don't. In fact, we've already passed it, so it should have been. I'll do it here. Example 2. Calculate the limit. Oh. The limit. Goodness gracious. This pen was right down next to my fan exhaust. It's not too hot to touch, but it's almost uncomfortably hot. Okay. Calculate the limit as x goes to infinity of 20x squared minus 3x over 3x to the fifth minus 4x squared plus 5. Now, all we're interested in for very, 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 very large x's is x is going, and actually it's only going to positive infinity. Second, 20x squared in the numerator and 3x to the fifth in the denominator. Those are your leading terms. So basically what we do is this will then be the limit as x goes to infinity of 20x squared over 3x to the fifth. Okay? Now, if you don't want to mess with your 20 and the 3, you can pull those out and make it 20/3, the limit as x approaches infinity of x squared over x to the fifth. Well, guess what? X squared will go into x squared one time, and x squared will go into x to the fifth x cubed times. So this is 20/3 times the limit as x goes to infinity of 1 over x cubed. And you know what? Guess what? It doesn't matter that 20/3 in front. Doesn't matter anything else. The limit as x is getting extraordinarily large of 1 over x cubed, a huge number, cubed, that's going to be even bigger. Okay. I'm sorry. Okay. This is x squared up here. This is x fifth up here, right? This is x times x. This is x times x times x times x down. Yeah. In fact, you could write that as x to the minus 3, rather than 1 over x cubed. But guess what? As x gets large, x cubed gets even larger, and that the denominator getting large, numerator 1, is going really rapidly towards 0. So it doesn't matter about this 20/3 at all. That's going to 0. Okay? That's going to 0. Okay? And they went through all kinds of gyrations to get there. Okay? But actually they did do what I was suggesting doing, getting that into another form, but it's still fine. It's going to 0. Actually, we did that before we did theorem 2. That was interesting. So let's do example 3. I hadn't planned to do these, but these are applications that are, I think, pretty important. So I think what I will do is erase that ink first. Oh, I should have asked. Were you through with it? Okay. Example 3, 2 limits. The first limit, the limit is x is going to infinity. I believe it's a positive infinity. Of 3x to the 7 halves plus 7x to the minus 1 half over x squared minus x to the 1 half power. Okay. Now, again, it doesn't matter what's happening to the low powers of x. It's only the leading terms. Now, these are weird leading terms. This is not a rational expression, okay? Get that. It's not a rational expression because you have non-integral exponents. But still, the principle is still true, okay? Take just the leading terms. And that's going to be the limit of, as x approaches infinity, of 3x to the 7/2 over x squared. Okay? Because the smaller ones, they just give you noise in the middle. For very large values of x, the big exponents dominate. Okay? In fact, this is going to 0 anyway, isn't it? For very large x's, 7 over x squared is going to 0. But forget about that. This is going up so slowly compared to this is going up really, really rapidly. This wins. So just use your leading terms. Okay? Now, factor out the coefficients. That's just going to be 3 times the limit as x approaches infinity of x to the 7/2 over x squared. Okay? Now, this is a little harder to do. Well, it's not hard to do if you use the rules for exponents. Basically, x squared would be x to the 4/2, right? Because 2 is 4 over 2. Okay. So this would be 3 times the limit as x approaches infinity of x to the 3/2, right? That's a pretty ugly 2 there, but that is a half there. Okay. 7/2 minus 4/2 is 3/2. X to the 3/2 power. And guess what? That n is greater than 1. In fact, it's greater than 0. And the limit as x approaches infinity of any x raised to any power, positive power, is going to go to infinity. So this is going, which it increases without bounds. That's why I don't like doing this. It's going to infinity. Okay? Now let's do the B one. The limit as x is going to infinity of x squared over the square root of x cubed plus 1. The square root of x cubed plus 1. All right. Now this one may not be quite as obvious. In fact, I would say it's not quite as obvious. Okay? But I would say this. As x is going to infinity, this 1 has less and less value, meaning. It has a value of 1, but if x is going bigger and bigger and bigger, like when x is 10, this would already be the square root of 1,001. If x was 100, this would be 1,000,001. So guess what? That's going close to the x to the 3/2 power. Okay? And this probably isn't rigorous for mathematics, but I think it will do. And because that numerator is larger, that the whole value is less than. So this is less than the limit as, and it's not by much. In fact, I think you could say is equal to the limit of x squared over x to the 3/2 power. Okay? Because the square root, and this would then be, again, this would be 4/2, 3/2 be the limit as x approaches infinity of x to the 1/2 power. And according to our very first thing, any n greater than 0, 1/2 is greater than 0, that's going to infinity. Okay? So this is heading toward increasing without bound. Okay? Now They did it another way, which is perfectly fine. In fact, probably a little more rigorous. Okay? They take the maximum exponent of any of these forms that you have here, and that would be x to the 3/2 power, just like we did there too. And then they do x squared over x to the 3/2 power over the square root of x cubed over what's that? Same way I did before. If you look at maximum exponents, this is x squared. This would be this thing to the 3/2 power, to the 1/2 power. Well, this x cubed to the 1/2 power would be x to the 3/2 power. Again, I said the same thing up here. Well, I didn't, no, right here. I said this thing is greater than x to the 3/2 power, not by much, by infinitesimal amount. And in the long run, as x is larger and larger, that's approaching the same thing. And this is, the square root is to the 1/2 power, and this is x cubed to the 1/2 power. So x to the 3/2 power. And so they're doing the same thing. Since this is a maximum radical here, we're going to divide this x by x cubed and this by x cubed, okay? What are you dividing by? You're dividing by the square root of x cubed, which is x to the 3/2 power, so that's why you do this. So this will be by x cubed, and this will be plus 1 to the x cubed, okay? Now, if you do that and take the limit, this again will be x to the 1/2 power, okay? Just like we did before, and this would be the square root of 1 plus 1 over x cubed, and as x goes very large, this is going to 0. So that would just give you something going to infinity over something going to 1. Okay. And then let's look at example 4. Again, I hadn't planned to do these, but they are techniques that are used a lot, so I'm probably not going to test you on them, but I'll have to see. I can't remember. It's been a while since I made out the test, so I don't remember. I thought I skipped this section, but let's see. Here's your f of x. Calculate the limits at infinity of this f of x. So you're looking for the limit. Well, maybe we should just, x going to infinity of 12x plus 25 divided by the square root of 16x squared plus 100x plus 500. So they put some pretty big numbers in here. And basically, we're going to do sort of the same thing we did before. Let's divide everything down here inside the radical by x squared, the maximum exponent. So that was dividing by 1 over, or multiplying by 1 over x squared. So the square root of 1 over x squared, which is, square root of 1 over x squared is square root of x, right? Okay. So that would be dividing this by x and dividing this by x. Same thing, okay? Doing it the same thing, numerator and denominator, it's legal. This goes to 12. This goes to 0. As x goes to infinity, 25 over x is going to 0, right? But this is going to 12. Down here, this is going to 1. So this is going to the square root of 16, which is 4. This is going to 100 over x, but as x is getting infinitely large, like 1,000 or 1,000,000 or something, that's going to 0. Okay? So this is going to 0. And 500 over x squared, for any x greater than 100. 100 squared is 10,000. So that's going to 0. And you can get just as big as you want. Well, the square root of 16 is 4, so this comes up being 12. That goes to 0, that goes to 0, over 4, and that's equal to 3. Okay? Whoa! Oh my goodness, I didn't read the problem right. In fact, I didn't read the problem. No? Oh, wait. Yeah, 3. I went to positive infinity. But it says, what if x was negative? And notice here it didn't say. It says calculate the limits at infinity. That's what I didn't read. So they wanted the limit as x goes to positive infinity, we just did. But if you let it go to x go to negative infinity, everything turns out the same except as x is going to negative infinity, yeah, this is a little tricky, and I'm definitely not going to ask you anything like this on the test, but technically what you're doing here is dividing by the square root of 1 over x squared, or you're multiplying by the square root of 1 over x squared. But if x is negative, square root of 1 over x squared would be 1 over x. But if x is negative, you're just divided by a negative number. So that makes the denominator negative. Now, they claim it doesn't make the numerator negative. Yeah. The only place it has a value there is in the denominator, and that would be what to 0 from negative side. So that would be, so if you went to negative infinity, and I didn't read that when I was doing it, so limits, that would be a negative 3. But again, don't sweat it, but this sure lets you see it. If you graph that function we're just talking about, here is the graph. Now, I don't usually graph these things, but I was just thinking they were letting it go to positive infinity because I didn't read the problem well. But sure enough, it's going to 3. But if you let it go to negative infinity, it actually is going to negative 3. It actually dips below negative 3 and then comes back up. Now, the only reason I'm even messing with this, I'd just say, forget it, you're not going to have one like it. What is your major, by the way? Biomedical what? Oh, biomedical science. I wouldn't be surprised if you might not hit this again. This is called a logistic curve. Quite often in biological sciences, for instance, now, again, this is going to make a lot of sense, but you'll run into curves like this, not with negative numbers in them, but you run into curves like this, but translate everything up here. Let's say an epidemic, such as Ebola in Liberia a couple summers ago. Remember that? It was just getting incredibly out of control. And again, you don't have any negative numbers in that. They're all positive. But when the incident rate was very low, you had very little exposure, so the disease spread very slowly. But once you reach some kind of like a critical amount, that more people were getting exposed, then the infection rate went up like crazy. Now, if it had been allowed to go on, now Ebola was a deadly disease, after a while, everybody's either going to have immunity to it or going to be dead. So it's going to reach all your population. And then the rate is going to slow down because everybody is either dead or immune to it. So diseases follow these logistic curves. So going to infinities, somewhere back there, no one was exposed to it, or maybe just one person got exposed. But then it may have been a very slow rise, but then at some point it just took off. And then, some diseases, the logistic curve may be more slanted, so that it may be a lot slower in progressing. Ebola was one that, when it took off very, very fast. But other things will do the same thing too. So the only reason I'm going to mention it is that's your major. You might actually see. Again, the scales won't be right on this, but you'll see these kind of curves, perhaps, in the future. And when you are analyzing them, my wife is an epidemiologist. She studies diseases, epidemics, you might think of, and she does logistic regression all the time. That's the main tool that she uses in her analysis of thing. I say that. I don't know if it really is her main tool, but it seems like she uses that more than others. Okay. I'm not going to assign any homework exercises here, but if you feel like you'd like to look at some of these, knock yourself out. Odd number answers are in the back. But I did want to say on question number 33, according to the Michaelis-Menten equation, and they give that in figure 7. Well, no, figure 7 isn't the equation. It's pictures of Leonore Michaelis, okay, who lived from 1875 to 1949, the year my older brother was born, and Maud Menten, she was born 4 years after him, but she lived 11 years longer. They came up with an equation, which is biomedical science. When an enzyme is combined with a substrate of concentration S in millimolars, which is a biological, well, it's a chemical type term there, the reaction rate in micromolars per minute is this rate here. So here are two people. These are Canadian-born biochemist Maud Menten, is best known for her fundamental work on enzyme kinetics with the German scientist Leonore Michaelis. She was also an accomplished painter, clarinetist, mountain climber, and master of numerous languages. Quite a Renaissance woman who lived from shortly after the end of, she was from Canada, but the end of our war between the states, Civil War, that was ended in 1864. So it was 15 years after that war was over, up until 1960, the year Kennedy was elected president. And she did groundbreaking work. Pretty impressive for a woman of that, in that age. And then the Michaelis. So you're certainly welcome to use either of those as paper topics, or how did they develop this, or what are the practical uses of this. You can go several directions there. But I did want to point that out. What's that? Yeah, excellent. All right, let's move. I think that's the last slide. So let's move on to, I didn't intend to spend that long on 2.7, but it did have, and especially since your major is related to some of that, I thought it was worth doing a little bit there. Well, maybe 2.8 won't open. Here it comes. All right, we'll do it from the current slide. Now, I'll zoom in to begin with, but I'll probably have to zoom out not too much later. Okay. The intermediate value theorem, which is a topic of 2.8, and quite often mathematics, IVT is a very well-used theorem. IVT, intermediate value theorem, says, roughly speaking, that a continuous function, this is a continuous function, one on the left. That is not a continuous function. Okay? Remember? Okay. So, for a continuous function, cannot skip values. Okay? Consider a plane that takes off and climbs from 0 to 10,000 meters in 20 minutes. I sure don't want to be in a plane that takes off and then jumps suddenly up there. I think I'd be airsick like crazy, okay? It can't happen. It may be a gradual thing. It may take a long time for it to get going. It may go rapidly. It may slow down its descent before it keeps going. But it's going to travel from 0 to 10,000 meters in 20 minutes. And that shows it doing that. Okay? That plane cannot skip any altitude. It's got to go through every level. It's a continuous function. It may have fits and starts where it's changing curvature rapidly or reasonably, but it can't skip any points. Whereas the greatest integer function skips all the values on the y-axis that are not integers. It just jumps right over them. Every time it gets to the integer, it jumps up the whole integer. Definitely is skipping a lot of y values. This one can't skip any y values. Okay? So we have to assume in this thing not only if we knew this, that the plane starts at altitude 0 and makes it to 10,000 20 minutes later, somewhere, sometime in those 20 minutes, at least one time, it had to be at altitude, what was that? 6,582 feet, 0.52 feet. It doesn't matter. For any value here, sometime during that time interval, it had to take on every value between 0 and 10,000. This one, that one, that one, had to at least once. Now, if the plane had gone up, encountered turbulence, came back down, found a better spot, went up again, then it may have attained that more than once. But it's got to attain it at least once. It can't skip any values. Okay. So, that graph shows us, monotonically increasing. So it only meets it once, but it has to. By contrast, a discontinuous function can skip values, like this one. Here's your greatest integer function. If you had 1.5, no values of that, even though this is defined on all real numbers for x, the y's are not. Only have integral values there, so 1.5 being a fractional value, decimal value, not an integral value, missing it completely. Okay? So continuous functions, every value between the limits has to be met at least once, not true for discontinuous functions. Okay. So that leads to the intermediate value theorem, which is what this section is focusing on. If you'll excuse me just a minute, I've got to get another swig of water. Helps my throat. All right, here's the intermediate value theorem. Condition is your function must be continuous. So if f of x is continuous, it doesn't have to be continuous everywhere. It has to be continuous on some closed interval, a to b, closed meaning you count the a and the b in the interval, and f of A is not equal to f of B. They're not the same at the endpoints, but f is continuous everywhere between those values. Then for every value m that's in between f of A and f of B, there exists at least one value c somewhere on this interval A to B, such that f of c is equal to that m. Okay? Now, let's go back to our first thing here. I guess I'll blow them up again. All right. Here, our interval was from 0 to 20. Okay? And sure enough, the function is continuous on that interval 0 to 20. Okay? It's, here's your f of 0, here's your f of 20. Okay? They're not the same. Okay? That was a requirement. F of A cannot equal f of B. They're not. Here's f of A is 0, f of 20 was 10,000. Okay? So, for every value in between 0 and 10,000, any m value that's in between those, there's some place in between A and B that has that value. For this m, it was that one. For an m right here, it would be that one. For an m up here, it would be that one. Okay? But for every value m in between 0 and 10,000, there's at least one point c in between 0 and 20, where alpha c is equal to that m. Now, notice here, if we took our interval small enough and said between 1 and 1.9, say, that is a continuous function on that interval. But alpha of 1 is equal to alpha of 1.9. So it doesn't fit the criteria. It has to have different values at the endpoint. This one doesn't. To get to a different value, you have to go up here, but guess what? It's not continuous then. So this would not ever fit. And the reason basically is twofold. In the first case, the second function wasn't continuous everywhere, but if you use the small enough closed interval, it would be continuous there, but f of A was equal to f of B on that place where it was continuous, so it didn't fit. The other one fit in every case. It was continuous from 0 to 20, so it fits in there. F of 0 was not equal to f of 20, it fits there. And then for any value m in between f of A and f of B that was 0 and 10,000, there exists at least one value c, they call it T0, that's in between 0 and 20, such that alpha c is exactly equal to m. All right, that seems like it makes kind of perfect sense, doesn't it? Okay? Here's another function. Okay? Here is the sine function from 0 to pi halves. Okay? Is it a continuous function? Yes. The range is going from 0 to 1. The domain is going 0 to pi halves. The range is going 0 to 1. And f of 0 is not equal to f of pi halves. Okay? So we're fine there. So for every value between 0 and 1, like 0.3, 0.01, 0.957, every point in between there is at least one point C where those values would cross the graph. And there would be something in between 0 and pi halves such that every point, at 0.3 for instance, there it is. there's a C. We don't know what the value is, but you could calculate it. Okay. Uh-oh. We just did example 1. I thought this was just a figure. This was example 1. Prove that the equation sine x equal 0.3. Oops. Yuck. Sine x equals 0.3. Okay? Prove that that equation has at least one solution. So how do they prove it? All they need is one solution. So pick an interval that you figure is going to have that solution. I wouldn't have picked negative pi halves to 0. That would have had a value 0.3. So pick an interval that your function takes on values less than 0.3 up to something greater than 0.3. Why not 0 to pi halves? That goes from 0 to 1. It's got to. So pick an interval, any interval that contains that. We did, and that is a continuous function. The f of 0 is not equal to f of pi halves. Sine of 0 is 0. Sine of pi halves is 1. 0.3 is in between 0 and 1, so there's got to be some value there. We don't know what it is, but you can do it if you have a calculator. So that's all there was to that. The intermediate value theorem can be used to show the existence of zeros of functions. If f is a continuous function, it takes on both positive and negative values. Say f of a is less than 0, f of b is greater than 0, then the intermediate value function guarantees there's some c in between a and b such that f of c is equal to 0. The head is clogging up, and actually cold water is not helping it any. It's actually making it clog worse. I'm not as dry, but my head's clogging up. So here, I think, comes a corollary. I guess since it was theorem 1, this is corollary 2. It seems kind of crazy. It seems like this would be corollary 1, since you didn't have 1 before. But I guess the theorem 1, corollary 2, whatever. Existence of zeros. If f of x is a continuous function on this interval a to b, and if f of a and f of b are both non-zero and have opposite signs, f of a could be negative, f of b positive, or f of a negative and f of b positive. It doesn't matter which, but they just have to have opposite signs. Then you're guaranteed that f of x has a 0 because it is a continuous function. You can't get from here to there without crossing the x-axis. Guaranteed to have a 0 somewhere in that interval a to b. They have different signs, and neither one of them are 0. Then there's got to be a 0 in between. Doesn't say there's only one. There's got to be at least one. Now, we can locate zeros of every function to arbitrary accuracy by using the bisection method. Okay? I think you've probably done something like this before. Can't write on this as long as... Sorry. Okay. Here happens to be a graph of f of x equals cosine squared x minus 2 times the sine of x over 4. What a nice little function. Okay. Obviously, when x is equal to 0, Cosine of 0 is 1. So 1 squared is 1. Sine of 0, well, 0 over 4 is still 0. Sine of 0 is 0. So this would be 1. Starts off at 1 up here. Okay. Now, somewhere over here, sorry. Man. Somewhere over here, alpha of x goes negative. Now, where would that occur? Well, you notice cosine stays positive. Well, cosine alternates positive and negative, but cosine squared is always going to be positive. So all we need to do is get cosine to be a small number, like getting close to pi halves, because at pi halves, cosine is 0. Okay? Well, if cosine is 0, somewhere around pi halves is about 1.57. So now cosine squared is pretty small. But what we have to do is get sine to be also a negative number, and then minus 2 times a negative, sine to be a positive number, and as long as we can get that greater than this, then we're going to guarantee that goes negative. Well, the graph shows that it does, and it shows it does, it's negative at 1 and at 2. So you can use either one of those you want. You know what? I'm doing example 2. Let's do example 2. I didn't realize. I thought this was just an illustration. This is actually an example. So let me back up and do example 2. Show that f of x, well, here it is here. There's your f of x. Okay? Show that that has a 0 in the interval 0 to 2. Okay? Then locate the 0 more accurately by the bisection method. Okay? Okay. Now, they haven't really explained it all that well, but what does bisection mean to you? Cut it in two, basically, right? In other words, take half of it. Okay? So, it's going to take, and they call it midpoint, same thing. So, using a calculator, we're going to do this. So, the first thing you got to do is make sure, pull out your calculator. Now, what mode did you better be in? We talked about taking sines and cosines. Do that. Angles. Second, radian mode. Make sure you're in radian mode. And just for funsies, even though I've already done it for you, do, now I don't know how well versed you are on your calculator, but if you can do f of x equal cosine squared x minus 2 sine x over 4, and plug in x equals 0, you'll see that comes out 1. Okay. And if you plug in 2, you'll see it comes out a negative value. I don't know what it is, but it's going to be a negative value. Okay? Now, they give it in the book as negative 0.786. So we know there is a 0 between 0 and 2. Positive here, negative here. So let's take half the way, 1. So do alpha of 1. Plug in 1 to that value. You do that, you'll see that it's also negative. Right? Okay. You can just plug it in if you want to. Cosine squared of 1 minus 2 times sine of 0.25. You'll see that comes out being negative also, right? Okay. Got it? What's that? I still do. Oh, it will not. Huh? Which kind do you have? Yeah. Okay. That. Okay. Right after you do cosine. Okay. Cosine. Now do x squared. We'll do anything else. Cosine. I'll do the x squared. There. That's what it is. Oh man. Okay. I know that it'll do this. Back up again. Do cosine x, I guess. What did we do before? Close that out. Parentheses times cosine x. And now do minus 2 sine, and then you have put the x over 4 before you put it up. That would work. Right. There's got to be a way to make it square, but I don't know what that is. Okay. Now, at that point, okay, just for funsies, check it and see if you put x equal 1, if you get 1. I mean, x equals 0, you get 1. You get put it what? Yeah. Yeah, that was down here. Did you put in a 0 for x? Did you get 1?
Yes.
Okay. When you put in 2, you got what they get in the book, negative 0.786 or something like that. Okay. Then you put in 1, and what do you get? Negative 0.203, right? Okay. Now, so you know it's between 0 and 1 now, because it's positive here and negative here. So put in a half. .521. Perfect. Okay, so now you know it's between a half and 1, right? So it's positive here and negative there. So put in 3/4. 175. Okay. Okay, and that's still positive. Okay. 1.163. Okay. So then do point. That was 0.75. What would that be? 7/8. It's in between 3/4 and 1. 7/8 is 0.885, isn't it? All right, you're getting pretty close, okay? Negative 0.0231, okay? Well, now you know it's between 3/4 and 7/8, okay? So you can keep taking half of each time, and from now on, you're going to have smaller and smaller, I mean, not every time smaller and smaller numbers, but if you keep doing it, you're going to find out you're going to keep getting smaller and smaller until you say, you know, that's close enough, okay? 0.00025 or something like that, that's close enough. It's going to be close to that. All right. So, we conclude F does have a 0, satisfying that between 0.75 and 0.875. Okay. Sorry. All right. The intermediate value theorem seems to state the obvious, namely that the continuous function cannot skip values. Yet its proof is subtle because it depends on the completeness property of real numbers. I'll let you read that. We're not doing it. If you want to see that, it's at Appendix B at the back of the book. Now, do you want to do preliminary questions? Do you like doing those? Do you find them useful or not? Do them? Okay. Well, no, we can't, can we? Isn't it 11:10? Oh, 11:08. We got 2 more minutes. Let's see if we can get one done anyway. Prove that f of x equal x squared, I've already written it here, f of x equal x squared takes on the value 0.5 on the interval 0 to 1. Now, all you have to do is prove that it takes on that value. How do you prove it? Plug in a 0. What do you get? Oh, you can do it in your head. 0. And plug in a 1. 1. Guess what? That proves it has to take. Okay, first, f of x equal x squared is a continuous function because it's a polynomial. Okay? The squaring function. Okay? And you've shown that f of 0 is 0, f of 1 is 1. There's got to be some value in between 0 and 1 that is 0.5. You don't have to show what it is, just the intermediate value proves that's the case. Okay? Let's see if they did it quite that simply. That was awfully simple-minded, but that's all it asked for. 2.7, wait, this is 2.8, isn't it? Yeah. 2.8 preliminary question says, observe that f of x equal x squared is continuous on 0, 1, with f of 0 is equal to 0, f of 1, 1, because f of 0 is less than 0.5, f of 1 is greater than 0.5, intermediate value theorem guarantees there is some c in there such that f of c is, that's all you have to do. You didn't have to find what value, just that it existed. Okay. And that probably used our 2 minutes, didn't it? Okay. So, do you want to try to do preliminary questions on your own, or do you want me to start with those next time when we start class? Okay. So we will start next time on the formal definition of a limit. This is 2.9. And I think what we'll do for 2.9 is just like we did for 2.7. I think I'll go over this, give you the slideshow on it, but I won't guarantee there won't be a question on it, but I think you'll see there'll be, if there is a question on it, it's going to be pretty straightforward. We'll work a couple of the examples for you. But this finishes, I think, yes, Chapter 2. I wish I had already run off the test. I didn't think we would finish this much today, but I will run off the test and have those ready for you on Monday. Okay? Because there may be a question or two on 2.9, so we'll do that. We'll pick up then at 2.9 and go from here. Good deal. Good class. Glad you came. I get rather bored talking to myself, so I'm glad you were here. What's that? I can't hear. Oh yeah, I was still teaching away. You know, I just do it all on the Screencast-O-Matic, which goes to YouTube. So yeah, the folks who weren't here, they're responsible for it. That's why I record the class, so they don't have to get it just out of the book. They may find the book easier,